Today we are going to see a review of curvilinear motion. What equations controlled when bodies, and in our interest here, in case vehicles go through when they take turns. What equations are control the motions of those? That's what we're going to see. All right. So we have this objective. We will be able to determine the normal and tangential components of the velocity and acceleration of a particle traveling along a curved path. Like in the example in here, we have a set of boxes that are going to go on this set of rollers on this curve, and obviously the boxes will be subject to curvilinear motion. And if we consider that a vector is a mixture of the magnitude and direction, whether the direction of the or the magnitude changes, it produces an acceleration, because the acceleration is the change of the velocity with respect to time. So as dv dt is the acceleration. So what I'm saying is, if we change the velocity and we change the magnitude, yeah, we have an acceleration. But if we change just the magnitude, or we change just the direction, we still will get a different kind of acceleration. Okay, so here we're gonna go mainly on studying the normal and tangential components of the velocity and acceleration. So let's say here you have a this is perfect for what we're doing. You have a freeway, and a vehicle can take the turn this way and go this way, or it's coming from here and go around, go this way, or coming this way, goes around and then goes in the if we let's call this north direction, south, east and west, east and west. So this gives us a perfect setup in here, that cars traveling on this interchange experience an acceleration due to the changing speed, as well as due to the changing direction of the velocity. You see what I'm trying to say? Okay, if the speed um, is increasing at a known rate as it travels along the curve, how can we determine the magnitude and direction of its total acceleration? Because you see, what I'm trying to say is that the change of magnitude causes acceleration, the change of direction causes acceleration. So Hibbeler is putting this question here. He says, how can we determine the magnitude and direction, and this word is important, of its total acceleration? You see, if the vector is a velocity is a vector, then the acceleration is a vector. When we talk about total acceleration, we just don't add numbers. We are add vectors. I think please keep that in mind. All right. Why do we care about the total acceleration of the car? Let's see. What do you think? How come we care about the total acceleration of a car? The reason is that the acceleration is directly related to the force. You see, and that's what's important. Okay, let's take a look at this. A motorcycle um, travels uphill, and then you have this path, and it's gonna follow this function y equals f of x. In this case, the motorcycle is going on a curved path. And you may say, look, maybe that curved path coincides with the equation of a parabola of the type y is equal to 0.5 x squared. That's the type of equation that the profile of the motorcycle is going to follow. So if the motorcycle starts from rest and increases at a constant rate, meaning the speed is, how can we determine its velocity and acceleration at the top of the hill? Now, I think that we should make a clarification here. What's speed and what is velocity? Because we don't want to get these terms confused. The speed is actually the magnitude of the velocity. So like when you know, what speed where you were going, 40 miles an hour, is just the magnitude of the velocity. It does not include the direction. But when we use the term velocity, it includes magnitude and direction. Okay, so let's just have that clear. So if it increases at a constant rate, can we determine its velocity and acceleration at the top of the hill? How would you analyze the motorcycle's flight at the top of the hill? You see, that's he's going to become airborne. So, like in many situations in vehicle reconstruction, you deal with people with vehicles that become airborne. All right. So when the particle moves along a curved path, it is important to use other than Cartesian coordinates. When the path is known, normal and tangential coordinates are often used. Yeah. So this you could use polar coordinates, but in here if we have the particle in here and it's traveling around this curved path, you're going to have a component of the change of the acceleration in the direction of the travel plus a component, a normal component. The one that is in direction of travel is called tangential acceleration, and the one on the towards the u is the normal, and in the velocity case also tangential velocity. Okay, so when the origin is located on the particle and the origin moves with the particle, so we want to begin talking about the rotating frame, meaning a frame that is attached to the particle that moves or attached to the body that moves. So that is called the rotating frame. Also is known as a body coordinate system. So whenever you see either one of these terms that I'm telling you, you know it always refers to a coordinate system attached to the particle or the body in motion. Very good. The author has put here the t-axis for tangential to the path to the curve at the instant considered, positive in the direction of motion and n is the perpendicular to the axis, which is positive direction towards the center of curvature of the curve. Okay? So let's talk about the normal and tangential components. When the body goes into changing the path, instantaneously the body rotates about a point. So it may rotate about this point, may rotate about this point, and may rotate the other way around this point when you change directions. It's helpful to define these changes by so-called unit vectors. So unit vectors like you see on this graph, u normal and u tangential. That's how indicate the direction. So the center of curvature is at the O prime. See, it always lies on the concave side of the curve. Okay. So the radius of curvature is the perpendicular distance from the curve to the center of curvature at that point. That means that if you have it here, for example, the radius of curvature is the distance from the curve to the center. So if you have the curve here perpendicular, or you have the curve here perpendicular, that would be the so-called instantaneous center of rotation. Okay, the position of the particle at every instant of time is defined by the distance s along the curve and from a fixed reference point. So what I'm trying to tell you is that you could use rectangular coordinates and it would fit exactly what it says here, or you could use polar coordinates. The velocity vector is always tangent to the path of motion. Yeah? And the magnitude is determined by taking the time derivative of the path function. So you have that b is u times ut, where b is s dot or ds dt. So b defines the magnitude of the velocity, the speed. That's what I was saying. And you define the direction of the velocity vector. Alright. The acceleration is the time rate of change of the velocity. So the acceleration is dv dt, and this has, you see, if you have if you write down the velocity as a unit, it's a unit vector here, b times unit vector. If you take the derivative of that, you'll see is b dot times u plus b times u dot, meaning you're changing the magnitude or you're changing the direction. Here the b dot represents the change in the magnitude of the velocity, and u dot represents the rate of change in the direction. So that's that's how this works. The change of a vector is always um, affected by these two things. Um, let's see. I think it might be a good idea to perhaps take a little break and try to explain this a little better. So what we're going to do is, let me make a graph over here where we will see how we go about the let's see, let's get a new page here for doing this note. So let's just do a little explanation in here. So let's say that we have a situation where we can draw the axis here, like here, let's say, and then you have the other, let's say like this, yeah. And I am going to describe the position of a particle as it is, let's say, over here. Let's say it's right there at some point. But the particle also has a new point. So this is the point 1, and this is 2. Yeah. So if you look at the vector that joins both of these, and you say, okay, this vector is like this. Sorry. Trying to draw a straight line. And somehow I didn't click exactly, or did something not quite right. There you go. Okay. And I'm going to, okay, so this is the position of the vector first, right? This is the position that you have here. Yeah, that's the, and if you do the same thing with the second point, we're gonna go from here to here. Yeah, that's the second one. Yeah. I would like to show you that the vector, if you project this to be able to be in this position, has a change in the let's call it delta r direction there, and the perpendicular direction to it is the perpendicular direction to it is the other change. So this is delta r, this would be delta r times theta, right? Where this would be the change. This would be theta. It actually no. This is the change. Hold on for a second. We need to be precise on how we do this. I just need to erase the red, not the blue. Ah, can I do just to make it correct? All right. And if we do the final vector, we can draw it from the origin over here to here. Yeah. So this, you could say, is equal to the change in magnitude. Yeah. And this other one is equal to the change in direction. This one is the term delta r over delta t, delta r theta delta t. All right. So you could say, by doing graphically in here, if this is the vector p, let's say, if you have dp dt is equal to the change of p dp dt plus r, this would be r theta. You would say p times theta, but in this is really cross theta, the angular velocity in this case. So this is due to the change in magnitude, and this will be the change in direction. Okay, so this is what I want to show you, that where those terms come from. And this is, p cross theta dot. Where does that come from? The change, this change that you see in here, this change is perpendicular to the path, the original path. So that is omega cross r. But where r is the original vector, and dr is the change of this vector. And like I said, the derivative of a vector always has two components: one change in magnitude, one change in direction. Okay, let's go back. So if this is true, we have the the indication of what I was trying to tell you is that this is the change. This is, you say, delta magnitude, and this is delta direction. All right. So v dot represents the change in magnitude of the velocity, and u dot the change in the direction. Then if you look at this, the there is another way of saying this. You could do the change in the normal direction or change in the tangential direction. So this one This component is in the tangential direction, which would be the change of the velocity just by changing, by increasing or decreasing. This one has to do with the rotation, because we want this times the normal, so which will give us a drawing similar to what I did previously, right here. See that the change is perpendicular, and therefore in fact is a cross product. And if you want to put it in terms of the angular acceleration, because this term, this would be v squared over rho, and the result is the acceleration, total acceleration, would be a times u plus an times u times un. All right. So if we consider the change of the velocity in the same way, there will be two components of the acceleration. One that is the tangential acceleration, which is the tangent to the curve, and it's in the direction of increases or increase in velocity. And the other is the normal or centripetal component. Is always directed towards the center of curvature and a value v squared over r. The magnitude of the acceleration is in this square root of a1 squared over squared. Yeah, in the case of the acceleration vector. These are some special cases. Particle moves along a straight line. That means the radius of curvature is infinite, so the normal acceleration is 0. The tangential component represents the time rate of change in the magnitude of the velocity. So in this case, moving a straight line doesn't change the velocity just by the radius of curvature, which is infinite. 2, the particle moves along a curve at a constant speed. Yeah. If this is true, constant speed indicates that we will have a normal acceleration of value v squared over r. The normal component in this case of the forces represents the time rate of change in the direction of the velocity, which means the time rate of change of momentum. 3, the tangential component acceleration is constant. Okay, so if you have an acceleration that is constant, you will have that s is s0 plus v sub 0 t plus 1 half of at squared. We derived that equation last time. V is b o plus the acceleration, total acceleration. So b squared, again, that was one of the other equations that we need to learn. Is b0 squared plus 2ax. So the s0 and v0 in this equation are the initial position and velocity of the particle at time equals to 0. So this is important because these equations can be related to the projectile motion also. If you move a particle along a path expressed as a function of x and the radius of curvature at any point in the path can be calculated like this. This is to calculate the radius of curvature. So if you have motion in 3D, which we for the most part we are not going to see it right now, but later, because we want to do planar motion first. Nevertheless, it's important to look at the how you set up a three-dimensional problem. Here we have x, y, and z, and in here the body axis or coordinate that move with the body is this coordinate system here. The t-axis is tangent to the path and the n-axis points toward the center of curvature. The plane containing the end and t is called the osculating plane, or I would call it the operating plane in my, I'm going to make it a little easier. The third axis is defined, called the binomial axis, and it has the unit vector UP, and is directed perpendicular towards the plane, and in this sense is defined as the cross product. Same thing as I was trying to tell you a moment ago on how the cross product comes in. So if you have a little difficulty with the cross product or the dot product, I really encourage you to review those concepts on your own. Okay, here's an example. We have starting from rest, you have this motorboat travels around a circular path of 50 meters at the speed that increases with time of b is 0.2 t squared. The speed increases with time. The magnitudes find the magnitudes of the boat's velocity and acceleration at the instant t equals to 3 seconds. So how do we do this? This is the plan. The boat starts from rest when t is equal to 0. Then we have to say calculate the velocity at t equals to 3 seconds using the function that we're given. So the fact that you have 0.2 t squared, for sure this has an acceleration because it's the change of that velocity in time. So we calculate the velocity at 3 equals 3 seconds. And then we calculate the tangential and normal components of the acceleration, then the magnitude of the acceleration vector. Well, yeah, because if you know the components, all you have to do is to add those two vectors in vectorial form, and that's it. So what is the solution to the problem? Let's listen to the problem first. Start from rest. This motorboat travels around a circular path of 50 meters. This is the radius, radius of the curvature. At the speed that is increasing, that increases with time. At the speed that increases with time, of being b is equal to 0.2 t squared meters per second. And so we calculate the velocity using this equation. Then we calculate the tangential and normal components of the acceleration. And once we have the tangential and normal components of acceleration, then we need to do a vector sum and then we're done. So velocity vector is b times u, where the magnitude is given by 0.2 t squared at 3 seconds. So if that's the case, b is 1.8 meters per second. The acceleration vector is at times ut plus an times un. So it's about the same thing, about adding the tangential acceleration and adding the normal acceleration. This one right here, this is the tangential acceleration. Yes, and this one right here is the normal acceleration. Okay. The tangential components A1 would be the derivative of 2t squared, which is 0.4t meters per second squared. So that's the tangential component of the acceleration. At t equals to 3 seconds, at is 0.4t. Then we have at 3 seconds, at is 0.4t equals to 1.2 meters per second. That the normal component is there, b squared over r. We calculate that, and so the b is squared over r. And so once we have these two components, we can find out the magnitude of the acceleration by getting the resultant between those two. That's why we cannot sum algebraically, but you have to sum as two vectors. And that adds up to, okay, so this will have the acceleration of both of them. Let's take a break now.